Is retrieval augmented generation dead? Well, it depends on the use case. Recently, when I mentioned that I work with retrieval augmented generation, or RAG, I got told this approach is dead and completely replaced by LLMs that can read thousands of pages and answer questions directly from that content. That made me wonder if I was riding that horse and I should stop investing time in realizing a project with RAG. But as so often in life, things are more complex, and spoiler alert, the horse that I'm riding is still in very good shape. So, what is retrieval augmented generation very briefly? Text passages up to a certain length, let's say around 300 words, are converted through a mathematical operation into vectors. These vectors represent the semantic meaning of the text, not as words, but as points in a high-dimensional space, often with hundreds of dimensions. You can take a large set of text passages, transform each of them into a vector, and store them for later retrieval. When you want to find something, you type what you are looking for, and the query text is also converted into a vector. Next, the system searches across thousands of vectors to find the ones closest to your query vector. Each found vector points back to its original text passage, so you retrieve content that matches the meaning of your query, not just identical keywords. That's the key. The search is based on semantic similarity rather than exact search terms. And finally, an LLM formulates an answer to your question using just the returned text passages, which is much less text to process than the entire document. This technology has often been used to search across long documents by splitting them into chunks that are vectorized and then searched to identify relevant passages. For many long document use cases today, a capable LLM can handle this directly for an end user, so a classic RAG pipeline is no longer necessary. But my use case is different and not about that exact scenario, so let's first look at the use case in more detail. My use case is about finding categories for support tickets using text only. No thousands of fields that need to be filled in to classify and determine the category, just natural language understanding of the support tickets and the written category definitions. What is that good for? Here are two benefits. You can create statistics to identify and address major pain points, and you can help the people working with the tickets by suggesting how similar cases have been solved before. And what makes it different from searching a knowledge base for a documented issue, that is the category? Well, this approach is not about scrolling through search results, but about getting the correct category suggested with close to 100% precision. Let me walk you through the components that make up this solution in its simplest form before explaining how they work together. There are four main components plus an additional resource accessed via API. First, there are the data sources. For support ticket categorization, these are the support tickets themselves, which can come from any ticketing system such as ServiceNow, Zendesk, or similar platforms. As a second data source, you need a set of defined categories. For instance, this could be a SharePoint list that stores the text definition of each category. Second, a Snowflake database where two tables store the information from the two data sources in a format suitable for this solution. Number 3. The user interface is built using MS Power BI and Power Apps, providing a simple and accessible way to interact with the data. Fourth, Azure Databricks acts as the core engine, orchestrating all operations by executing Python scripts and SQL prompts. And finally, there's an additional resource, the Azure AI Foundry, which is accessed via API to execute large language model, or short LLM, prompts. Now it is time to understand how the data flows through this retrieval augmented generation use case for support ticket categorization. It starts with two ETL pipelines. The first pipeline for the support tickets is extremely simple. Relevant data, mainly the conversation and optionally the subject or similar fields, are written into the Snowflake database. The second ETL pipeline is more complex and has real tasks to handle in addition to cleansing the data. Here, the written information defining the categories is received by Databricks, where a prompt is constructed that requests a structured summarization of each category definition. It is important to emphasize that clearly specifying the expected output structure in the prompt is crucial for the overall quality of the solution. Azure AI Foundry executes the prompt and sends the result for vectorization, where Hugging Face installed in Databricks creates the embedding. Finally, all input data from the source, as well as the prompt result, and the vector embedding are stored in the relevant Snowflake table. Keeping all this data makes understanding and debugging the system much easier later on. The user interface in Microsoft Power BI fetches the tickets from the Snowflake table and displays them in a list that can be filtered based on the user's needs. When a ticket is selected from the list, the data for that specific ticket is passed to an embedded Microsoft Power App. From the Power App, the user can trigger a search for a matching category for the current ticket. To allow the algorithm to process the request, the conversation of the selected support ticket is then sent to Databricks. From here, the conversation becomes part of a LLM prompt that is sent to Azure AI Foundry for execution. The prompt requests a ticket summary that follows the same systematic output structure used earlier for the category summarization. The ticket summary is then sent to Hugging Face, where a vector embedding is created for further processing. Next, an approximate nearest neighbor, or ANN, calculation is performed between the ticket summary vector and all of the category summary vectors stored in the Snowflake category table, so that categories with high semantic similarity to the current ticket are returned. If all category descriptions and prompts are well written, the correct category should appear within the top 10 ANN matches. Having the correct match in the top 10 out of several thousand candidates is already strong, but the goal is to have the correct category in first position or at least in the top 3 in nearly 100% of searches. To reach that level of accuracy, one more processing step is required. The written text summaries of the top 10 categories are retrieved and passed together with a summary of the current ticket into another LLM prompt that asks the model to assign a match rating to each of the top 10 categories. When the top 10 list is then sorted by the LLM's ratings, the correct category appears in the first position in about 95% of cases. The very last step is to pass the sorted top list to Power Apps, where it is displayed to the end user so they can make the final judgment on whether the suggestion is appropriate and, if desired, assign the current ticket to the top matching category. That's it, the simplest approach I have found to achieve extremely accurate support ticket categorization. In terms of the LLM used, the system can even run on a model that is 1 or 2 years old. It's not so much about the model itself, but about designing a systematic output structure for the summaries and writing the prompt to achieve it. And yes, there are of course thousands of ways to optimize and further develop the solution, but that's not the topic of this video. Let's return to the initial question. Is retrieval augmented generation dead? Not in this case. There are 2 major reasons for that. First, cost. Using a latest generation LLM that can handle thousands of words becomes expensive when pasting in all category summaries again and again to judge each of thousands of support tickets. Second, accuracy. Even as models improve, there is still a risk that an LLM will miss details in an ultra-long prompt, and ongoing model revisions mean that what works well today might perform less reliably tomorrow. In contrast, my RAG approach, with clearly defined and human-understandable steps, keeps the technology under human control instead of letting it choose its own path.